In today's activity, we're going to look a little bit at the movement of electrons in the formation of ions and ionic compounds. Remember, we said before the break that oxidation is the loss of electrons from an atom. Oil rig, oxidation is loss, and reduction is the gain of electrons on an atom. And these are things that have to happen in a pair. If something is oxidized, another chemical species has to be reduced because the electrons have mass and must therefore be conserved. So in order to do that, let's think a little bit about what elements are low energy, the stable elements. That is, of course, the noble gases, helium, neon, argon, krypton, xenon, group AA, or 18. And if we look at that, we notice the pattern in their electron configurations. They're full. All of the orbitals have a pair of electrons. So for helium, which is our one exception to the pattern, the only orbital available is the 1s orbital, but it is filled, so it behaves very similarly to the rest of the noble gases. The rest of the noble gases have that full valence shell of S2p6. So using an example of neon, neon is 1s2, 2s2, 2p6. The other thing that we know that is very stable is, of course, ions. Ions are elements, atoms of an element that have gained or lost electrons. And the point of doing that is to get to the same number of electrons as a noble gas, because they will be isoelectronic. They will have the same stable electron configuration. They'll be in the same low energy state if they have the same number of electrons as a noble gas. So that would be lots of different things. We could use cations or positive ions for that, like magnesium. The magnesium atom has 12 electrons. The low energy stable magnesium ion has lost 2 to get to the same number of electrons as neon, 10. Since it's lost 2 electrons, it has 2 extra protons, 2 extra positive charges, and it's a 2+ cation. But I can also do this, of course, with gaining electrons and making a negative ion, an anion. For example, bromine. Bromine has 35 electrons, just 1 away from the noble gas configuration. So bromine tends to gain 1 electron to get to the same number as argon, 36. So remember where we're trying to go. We're trying to get to the same number of electrons as a noble gas, and we want to either lose or gain the fewest number of electrons that we can. So since we can't see atoms and ions and electrons, we're going to scale it up by about a billion jillion times to use some manipulables. We'll have some atoms and some electrons so we can hold them, touch them, feel them, and get a better notion of what happens when we form an ionic compound. So we have our various atoms, and we'll also have some small paper clips. And those small paper clips are going to be used to symbolize electrons. So in the envelope or little baggie, you have metallic elements, and they're already printed as their ion. Of course, each ion would have 8 electrons, the octet, the noble gas configuration, and each would have an appropriate positive charge. The non-metallic elements are printed as their atoms. So they have the normal valence number of electrons for that element. Chlorine is in group 7A. It should have 7 valence electrons, and you can see that there are 7 black dots around the rim of this atom. In order to become an ion, chlorine needs to gain an electron, because then it will have 18 electrons like argon. So in order to do this, we need to turn our ions into atoms so we can make a compound. And that means we need to add an electron to our positive metal ions. So for example, if I'm using lithium, it would come in the bag as lithium 1+. That means to make a lithium atom, I need to add back that valence electron because I know lithium should have 3 electrons. So I add a paperclip to this atom, and now I have 1s2, 2s1. I've added back that valence electron. So now I have lithium metal, and I can use it to make a compound. Today we are blowing up these atoms to giant size so that we can actually visualize what happens with the electrons when we form ions and make ionic compounds. That means the first thing we have to do is figure out exactly what will happen with the elements that we have. So I'll post this to you on Classroom and you can print it out or you can copy it into your lab notebook. But let's take a look at my example. My example here is lithium. And notice the directions say to put a number in either the gain or loss column. So there's nothing that does both. It's either gain or lose. With my example, lithium, when I look at the electrons gained column, the answer is none. Lithium is a metal and metals lose electrons. So how many electrons does lithium lose? Well, it's element number 3. It's got 3 electrons, which means the closest noble gas is helium. 2. I lose 1 electron to go from 3 electrons to 2 electrons. When I go to that noble gas configuration, then it's the configuration of helium, 1s2. And this would be lithium with a +1 charge. So to do another one here, for example, sodium. Okay, well, sodium does not gain electrons. It's a metal. Metals lose. Sodium is element number 11. The nearest noble gas is neon, with 10 electrons. So to go from 11 electrons to 10 electrons, again, we have to lose 1 electron. When we lose that 1 electron, we go from 11 electrons to 10 electrons. 10 electrons is the same as neon. And the resulting ion here would be sodium, which would also be +1. This really shouldn't be a surprise because lithium and sodium are both in the same group, and elements in a group behave similarly. When I get down to my nonmetals, where things are going to gain electrons, for example, oxygen is a nonmetal, and so it's going to gain some electrons, not lose. So you'll have to think, how many electrons should I gain in this case? And what noble gas will that be isoelectronic with? So I'm going to go ahead and have you complete this table either in your notes or on a printed copy of this, and make sure you show it to me when you come back to class.